I wanted to take a second and go through the example that we were talking about in class. We experienced some connectivity issues near the end, so I'd like to finish the example that we were discussing. If you recall, we were looking at the design of a simply supported beam with a uniformly distributed load where the bracing was provided only at the ends. So what we're going to be doing with this scenario is verifying the trial section. So let's just go ahead and get right into that. Okay. So the first thing that I'm going to do is I'm going to look at whether or not this section is going to be within Zone 1, Zone 2, or Zone 3. So what that means is that I'm going to need to look up some properties for the section that I'm analyzing. Now, a couple things to remember. First off, let me write up here on the top left. Let's put this over here. Let's recall we had determined that MU for this problem was 440.64 foot kips. And we had determined that VU was 73.44 kips. We had also determined that the trial section that we were verifying is an W18 by 76. Now, for the W18 by 76, the first thing I'm going to do is I'm going to look up the LP and the LR. Now, LP comes out, it's listed in the table as 9.22 feet, and LR is listed as 27.1 feet. Now, for this problem, LB was 24 feet. So that means we're in Zone 2 because we're between LP and LR. So therefore, I'm going to need a few more values from Table 3-2. I'm going to need phi MP, which for a W18 by 76 is 611. I'm going to need phi BF. Phi BF is 12.8 kips. And while I don't need it for an evaluation of moment capacity, I do need it for I do need phi VVN for an evaluation of shear capacity. Now, when you look this value up, it's 232 kips. Now, if you look at the, you can just look right here and see that phi VN is greater than VU. So obviously the shear capacity works. I'm going to list everything at the very end of the problem just to make sure that, that I'm consistent. Okay, first off, moment capacity. So what we're going to do is we've got all of our values listed. Recall also that we had MU, we had VU, and we also knew that CB was 1.14. We knew that because it was simply supported, it was uniformly distributed load, and it was braced only at the ends. And so we could look that up in Table 3.1. So first thing we're going to do is we're going to compute CB times phi MN, or sorry, phi MPX minus phi BF times LB minus LP. And so we're going to do that. So let's go ahead and chug that out. So this is 1.14 times 611 minus 12.8 kips times 24 feet minus 9.22 feet. And so when you chug that out, it comes out to 480.87 foot kips. So therefore, phi MN is the minimum of this quantity or phi MP. Remember, you always cut off your capacity at MP, which will become relevant extremely in our next lecture. So it's the minimum of all of this stuff, which we've already computed as 480.87, and then 611. And so this equals, obviously, 480.87 foot kips. Now, while it's not completely necessary, just to make sure that when I summarize my results for the problem that I'm being complete in my summary, I'm also going to go ahead and compute the live load deflection because there was a limit of the deflection on this problem of L over 360. I had verified that the W18 by 76 had the moment of inertia, but just again, just to make sure that my results are complete. So 5 WL to the fourth over 384 EI. So 5, and then WL, it was 3 kips per foot. L was 24 feet. That's being raised to the fourth. Now don't forget, in conventional units, we need our conversion factor. And then this is 384. 20,000. And then the moment of inertia for this problem was 1330, or well, I say for this problem, for the W18 by 76 is 1330. We had looked that up previously. And so last, let's chug this out. And so when you plug and chug these quantities, you get 0.581 inches. All right. And so if I want to summarize the problem, let's take it one step at a time. So phi Mn was 480.87 foot kips, and we compare that against Mu, which for this problem was 440.64. And so phi Mn is greater than or equal to Mu, so we're good. Next, phi VVN is 232, and VU is 73.44. Again, good. And also, as mentioned before, shear really never tends to be a really big problem with steel beams in buildings. In bridges, another story, but in buildings, not too bad. Now our allowable deflection, remember our allowable deflection for this problem was L over, I believe it was 240. Or no, sorry, L over 360. Sorry, it was L over 360. And so L over 360 was 0.8 inches, and then we have an actual deflection of 0.581. So with each condition, you know, we can withstand 480 foot kips of moment. We're only putting 440 on there. We can withstand 232 kips of shear. We're only putting 73 on there. We can withstand 0.8 inches of deflection, and it's only deflecting 0.581. And so therefore, using a W18 by 76, that is our answer. And a final note, just so that everybody's clear. At the beginning of the problem, when we computed Mu and we computed Vu, we found, or we started by assuming a beam self-weight. So our assumed self-weight was 100 pounds per foot. Well, the actual self-weight of a W18 by 76, well, it's a 76 pounds per foot. So what that means is we assumed that the beam is heavier than it actually is. So if the beam can withstand this Mu and this Vu as is, it can certainly withstand its own self-weight. We assumed that it weighed 100 pounds per foot, and the beam is strong enough to hold up 100 pounds per foot, so we don't need to update our moments and shears to reflect 76. We can if we would want an accurate or exact performance ratio, but it wouldn't change our design. Ultimately, the beam will still work. So I'll put here no need to update MU or VU. Now, if it was the other way around, if we assumed, let's say, the beam was 50 pounds per foot and it actually came out to be 76, well, then we would need to go through and compute a new MU and a new VU based on our new self-weight. But since the beam is lighter than what we assumed, there's no need to do that. That's all for this example. Like I said at the end of lecture, in our next design example, we'll look at what happens when CB gets particularly high, and it ultimately causes us to have to iterate a little bit in our designs. That's all I have. Everybody stay safe, and we'll see you next time.